Hello, everyone. I hope you hear me well online. Please raise your hands if you don't. So this is the very first seminar on OpenTPS, and when we organized the seminar, we said, let's do something small with just our two departments and our close collaborations. And we didn't realize that you would be more than maybe 30 people. So this is really great. Thank you so much for joining us today. I'm Sylvain Defay from MIRO, and I'm basically one of the main developers of OpenTPS. And today I'm with Sophie Wilkins from MIRO, Damien Danois from IC team, Guillaume Janssen from IBA, and Valentin Ahmed from IBA, previously from IC team. We made a very short demo 2 or 3 months ago, and some of you have seen this demo and would like to use OpenTPS to get started with it and maybe to contribute to it. But we also have a couple of people who don't know yet what OpenTPS can do. So we will first start with a general overview of OpenTPS. And then for the researchers, we will talk about the most important features that we have in OpenTPS, so those computation, time optimization, image processing tools, data augmentation, and we also talk about 4D treatment planning. So sometimes we will also focus on technical details, mainly for those who are already familiar with OpenTPS. So don't worry if you do not understand all the technical details, but do not hesitate to ask questions. I think the best moment to ask question is at the end of each part of this presentation. And for people online, you can also write question in the chat, and we'll read them at the end of each part. Yeah, and finally, a very important point today is that we will explain how to use OpenTPS, how to get started with it, and also how to contribute to it for those who want to contribute to OpenTPS. Yeah, so this is the very first seminar, so it won't be perfect. I want to emphasize this. We are also here to learn, so we are looking forward to your feedbacks. So please do not hesitate to contact us after the seminar to give a feedback on the seminar, but also on the OpenTPS platform. So in this very general introduction, I would like to emphasize 2 points. First, the rationale behind OpenTPS, the problem that we want to solve with OpenTPS, and also the spirit behind this research treatment planning system, which was made by researchers for researchers. This is very important. And I would like to start with an example that many researchers in the field of radiation therapy have faced. It's the prototyping of a new method. So let's imagine that you have a research idea, could be in the field of AI in radiation therapy, or you want to develop a new treatment planning method in radiation therapy. And for this, in this kind of situation, you generally first need to import data, which are in various formats. Usually it's in DICOM, but it might be other format. And then you want to pre-process them using usually Python tools like NumPy, SciPy, and sometimes you also want to apply more complex pre-processing. It could be image registration, deformable image registration. And then you also want to do things which are very specific to radiation therapy. For example, you want to convert your CT into stopping powers, compute this kind of physical quantity, because that's what matters for radiation therapy treatment planning. And then finally, after you've done all of this, you can develop your own idea. But that's not the end. Then you want to visualize the results, you want to assess the quality of the results. So you need dose computation, you need dose map visualization, and you also need DBHs. So that sort of things, right? And OpenTPS aims to simplify this workflow. OpenTPS aims to gather those important features which are always used in prototyping in radiation therapy in a single package. So we'll have a look at the features that we propose. But first, as I said, this research and planning system, it was designed by researchers, was coded by researchers from UC Louvain and IBA, and really for researchers. So first, written in Python, and we try to be as much modular and extendable as possible. And we also have this trade-off between code quality and simplicity, which is very important to us. We want everyone to understand the code, yet it's already significant application. So that's really this trade-off between quality and simplicity. This is our current team. So we have Damien Danois, the main developer from IC team. In MIRO, we have a couple of developers, and Sophie Workens in particular will present plan optimization today. And in IBA, there are currently 3 developers, and Guillaume Janssens and Valentin Ahmed will talk today a bit later. This might be the most important slide today. So the code is on GitLab. You have the link here. It's we made it public this week, so now everyone in the world can download the code. Everyone has access to the code, and there is also a website which we started to build. So it's a very preliminary website, but you will find a quick start on this website. OpenTPS is divided in 2 parts. We provide a library of functions, of features, and also of data classes. So in this library, the core library, you will find data classes, for example, for CT images, for RT plans, region of interest, but also CT calibrations, beam models, so everything which is the data. And we also have implemented a couple of methods to read and write data, so especially in DICOM ImageD format. Then we have a couple of data processing tools, image segmentation and registration, for example, and also a lot of methods related to radiation therapy. Proton dose computation and also proton plan optimization. So currently, everything which is in OpenTPS is for proton therapy, but I think that OpenTPS would be a very good tool for radiation therapy in general. It just needs to be extended to conventional radiation therapy. Then there is a second package in OpenTPS, and it's a graphical user interface, which can be used as a standalone application. So you can use it as a conventional treatment planning system. It's much more simple, but it's a standalone application. But you can also reuse, if you want, the building blocks of this graphical user interface to build new visualization tools. I would like to emphasize this, the reason behind this very clear separation. So it's 2 separate packages, and there is a very good reason for this. Obviously, it's a very good design choice, but not only. Most people usually need to run this kind of application on server because they want to do Monte Carlo computation, a lot of Monte Carlo computation. So they will go on clusters, and those server application, they cannot run the graphical user dependencies. So this would fail, and we don't want to deal with this kind of issue. So we clearly separated all the core library and the graphical user interface library. So you can run your application on any kind of computer or server. So in the graphical user interface, in this software, you will find also tools to import and export data. Not all data are supported yet. For example, you can import DICOM series such as CT images, but you cannot export them yet. But we will keep developing these features. Then, yeah, there is a lot of data visualization. Yeah, there is a couple of tools to crop for sample images, and there are applications very specific to the field of radiation therapy, plan optimization, and dose computation. And I would first like to start with a demo because there's a lot of slides, but you haven't seen the software yet. So what I propose is a very short demo of the graphical user interface, and then we will move on this presentation. Okay, so this. Yes, it's true. So we are connecting the screen here in the meeting room. Wonderful. So you should see the graphical user of OpenTPS that I launched from my IDE, which is PyCharm. You can import various kind of data. Here I will import a DICOM folder. So this folder is a CT, some RT-DOS. There is also an RT struct and an RT plan. This one. On the left, you have a couple of what we call a panel where you can design an RT plan, optimize a plan, perform dose computation, and you can also see the patient data. We provide several kinds of viewers. So this is just a standard image viewer on which we can see the CT image. We can also show the dose, the contours. For example, this CTV, but we also have DVH viewers. We have tools to draw profile, to check the dose on a profile. There is also 3D visualization, and you can play with stuff like window level, color maps, and so on. So that's just a very quick overview of the GUI, and today we will explain in much details how you can use it and how you can build application that runs in this software.
Oui, mais je dois faire recherche quand même.
So about the data viewers, so there are viewers for 2D images, 3D images, where we can, as I already shown, show a primary image, a secondary image, some contours, also the plan. I think I did not show the treatment plan, but you can show it. This 3D viewer for 3D images, which is not a resizing viewer, but a real 3D viewer. those profile DVHs, and we have colleagues working on dynamic image viewers for typically for so dynamic data, so like 4D CGs or fluoroscopy images. A very few technical details for the future developer of OpenTPS regarding the GUI. Everything is in PyQt, the layout, the widgets, the menu, the button, etc., and except for the graphs, which are made using PyQt graph, and the image visualization. All the image visualizations relies on VTK. If you download the code, the GUI package is divided in 3 main sections. One for the panels, this is what you see on the left, this for those computation, plan optimization. One for the tools, that's in the toolbar above, and one for the viewer with all the different image viewers that we have implemented. The core library is much different. So this is it does not depend on the GUI at all, and it really defines the method, the data classes, the algorithms, the methods to read, write data, and so on. And it can be used to build your own application, especially to build scripts, and then you can import your results in the GUI to visualize them and to assess the quality of your of the method that you would develop. Maybe what is the most important message here is this folder, OpenTPS core / examples. So we have an example section in the repository, and you will find a couple of examples, for instance, to optimize a treatment plan, to compute the dose. So I will have I will present a very short overview of all the sections in this core package. So there are the data classes. This is an overview of all the data classes that we have implemented. So we have implemented CT calibration. The CT calibration used by MC Square, which is a very specific format, and also that of ResStation. We also have data classes for all kinds of images, generic image like image 3D, but also CT image, deformation field, those image, LET map, region of interest, and so on. We have a data class for beam model or beam data library, DDL, for plan, for DVH, patient data, etc. If we look, for example, at the data class CT image, you can see that it inherits the image 3D data class, which is a generic class for 3D images with an origin, spacing, image array, orientation, and so on, which itself inherits patient data, which has 2 fields, the name of this data and a field patient. That as this patient data belongs to that patient. That's an example, and I think that this afternoon we could try a couple of these examples on your own computer. This shows how simple it is in OpenTPS to create a synthetic TT image, a synthetic region of interest, and to show this in the GUI. So in this case, I first create a patient, a dummy patient, then a CT image, which I fill with water. Let's say that water is alpha unit of 0 and air minus 1000. And then I create a region of interest, which is a binary mask in this case. And there is 2 additional lines which are not shown on this slide to show this in the graphical user interface. And you could, for example, perform those computation or plan optimization in the GUI based on those data. Same for the input-output methods. We have, for example, the method load data to load any kind of data which are supported by OpenTPS, like the folder I just downloaded, I've just shown before. And from this, you load the data in the patient list because there can be several patients in your folder. You can retrieve all the patients, and from the patient, you can retrieve, you can filter CT images, RT plans, and so on. And we have also read and write methods, for example, for CT calibration. Currently, that's what is shown on the right. Where we load a CT calibration and we use it to convert some RSP to units. The third section is the processing section. There are a couple of methods which are listed here. I won't present them all, especially because my colleagues will talk about the most important features later. And again, I think that what is most interesting is the example section that you find on the Git. As you see, we already provide examples for dose computation, image processing, plan optimization, registration, and so on. So, as I said, this afternoon, for those who want to stay with us this afternoon, there is a session dedicated to getting started with OpenTPS. We'll first install OpenTPS if it's not done yet. We'll give some help if there is some troubleshooting to do. And then we could benefit, we could use this session to try a couple of examples. For a simple example like this one, create a synthetic CT, a synthetic region of interest, and then use the graphical user interface to build a plan and to compute the dose. This was a very short overview of OpenTPS. I see there is no question in the chat for now. I don't know if in the room there is any question. Otherwise, we'll now start presenting the most interesting features, and we first start with proton dose computation.
We have one related to the exercise that you've just shown. So you said first, for example, we can create a synthetic CT and then their RI, and then use the GUI to make the optimization. The first part is synthetic CT creation, for example. Can you do that from the GUI as well, or this is typically from the core?
Okay, so the question is, can we use the core library in the GUI to create, for example, synthetic data or to launch computations from the GUI? I believe that's the question. So there are many ways to do. Usually, this in our lab, all people do is that they write their script with their methods using the core library, and at the end, they launch the GUI. But if you want to, in the GUI, you realize that you would like to do some additional stuff, we provide a scripting window in the GUI, which is very preliminary, from which you can use everything which is available in Python. But that's a good question, because the GUI it's a blocking operation, so you cannot perform code after in your main script. You have to close the GUI, and then it will run it blocks the main threads. Yeah, there is a scripting window. Okay. So in OpenTPS, you will find a dose engine, which is called MC². This is for proton dose computation. It was written by Kevin Souris when he was working in MIRO. And now he's working at IBA. He's still in the team of the developers of OpenTPS. So this is the typical workflow for those computation in OpenTPS. There is this dose computation module and MC square needs some config files, some beam models, CT image plan. And so those computation module will translate the data from OpenTPS to the format accepted by MC square, launch the MC square computation, which will output some dose image, but it might also be an LET image. And then this is imported by OpenTPS as a dose image in OpenTPS. And there are also a couple of tools like EA denoising, which has been developed, which is currently not part of the main OpenTPS distribution, just because of lack of time to put it back in, but we will do it later. And then, of course, the dose can also be exported if required. In the GUI, this is how it looks like in the GUI. You see the input, you need a CT, an RT plan. You can choose some simulation statistics if you want a very good quality on your dose distributions. You will use a lot of protons or very low uncertainty. And you also need the CT calibration and the beam model of your site. On the other hand, if you want to launch a Monte Carlo dose calculation from the core library, you see that you actually have much more options. You can, for example, compute beamlets, so the dose contribution of each pencil beam of a proton therapy treatment plan. Also compute the LET, and also there are also methods for robustness evaluation. And there are also a couple of additional properties. And for example, you can change the scoring spacing used to compute the dose and the simulation directory. In the GUI, this CT calibration and the beam model, this is usually you need to give your own CT calibration and beam model. So there is a default one in OpenTPS, so you can already start using OpenTPS with this default CT calibration, but of course you would have to provide your own CT calibration and beam model. This can be changed by the user, and in OpenTPS, this kind of modifications will be remembered by OpenTPS after it is closed. We use config file for this. In the core, you can do a Monte Carlo computation in 4 lines of code. This is how it looks like, and you would give the beam model directly. So you would use the IO method to read the beam model and the CT calibration, and you would give it to MC square dose calculator. You would also tell things like the number of primary particles that you want to use and compute the dose on the CT and the plan. This is very technical for people who would like to understand a bit how the code, the architecture of the code, and how we defined stuff in OpenTPS. As we expect to have more dose engines in OpenTPS in the future, we have written these abstract classes which define the templates to use the layout of your dose calculator. Typically, a dose calculator must have as input a CT calibration and a beam model, and they will provide a compute dose method. Dose influence calculator is for beamlets, and so MC square dose calculator implements those 2 abstract classes. And if you want to add another Monte Carlo dose calculator and you want it to work in OpenTPS, just have to implement those abstract classes. Yeah, you might wonder where the results are stored. For example, MC square will run, it will generate temporary files, it will generate results. Where is everything stored. This is in the OpenTPS workspace. So there is a default location when you first run OpenTPS. If we create a default folder, and the location is just in your home folder, it's called OpenTPS workspace, and there you will find the outputs of those computation, and also the input. It's interesting to know this, to sometimes just to understand, to debug, and you can change this default location, of course, if you wish. Okay, this was an overview of those computation. I see there is a couple of questions in the chat.
One of them was already answered. Yeah. But the other one is about the license. So can you, I don't know if Jens speaks about the license or.
Okay. True, I did not write any slide on the license. You will find the license on the GitLab, actually, and there are two licenses. The core library is fully open source. It's Apache 2.0 license. This means that you can do whatever you want with the core library. You can build your application. If you want to sell it, you can even sell it. That's a very permissive license. So you are actually, it's not even mandatory to have your code open source. So you can really do whatever you want. On the other hand, the graphical user interface is released under the GPL v3 license, or LGPL v3. I don't remember well. But this is not permissive, and because we were contaminated by Qt5. And so this is open source, but if you work in the GUI, all your derived work will have to be open source as well.
Yeah, and the following of the question was about are there any licenses for the dependent software? So there is this warning about the hobby.
Okay.
And NTMC.
Yes, true. So OpenTPS comes with several dependencies. Except those two licenses, which are not mentioned in the requirement list. All licenses are compatible with the OpenTPS license, but if you want to use some specific features in plan optimization, especially, you might want to download and get a license from Groovy. But this is if you want to use very specific features. For example, in plan optimization, Sophie will tell you that there are various algorithms. One is based on SciPy LBFGS. One is a homemade implementation of LBGS. There is also a beamlet implementation, and there is this linear programming implementation, and that one requires URB, for example, but you can still optimize the plan without URB.
Yes.
Wonderful. I don't know if in the audience here in Valada there is any question, otherwise, Sophie.
Okay, hello everybody. So as Sylvain said, I'm working mainly on the optimization part. So first, maybe a recap on what is the treatment planning optimization workflow in general in radiotherapy. So the first stage of planning is the spot selection, the spot placement. What does it mean is that you have your target in your patient and you have to place the spot in it because we are using pencil beam scanning. And so what we do is that we divide our target in different energy layers, depending on the depth inside the target in the patient. And then we have this grid of spots in each energy layers and we will irradiate spot by spot, layer by layer, and beam by beam. This stage is done using a ray tracing operation. This ray tracing was written in C, but was rapid with Python. Then, once we have this list of spots that have X and Y position, energies, Gantt triangle, etc., we can go to the second stage of the workflow, that is the beamlet calculation. What is a beamlet? The beamlet is the 3D dose distribution inside the patient. So each spot has a 3D dose distribution, and we need to simulate this dose. How do we do this? We use a dose engine that is MC square. Actually, it was written by Kevin Souris. And so this MC square engine, it will simulate the interactions of protons in the patient and will score the deposit dose in the spots. So at the end of this stage, we have this big beamlet matrix that has the number of lines correspond to the number of voxels in the patient, and the number of columns represent the number of spots. So now we can follow with the spot weight optimization. And the idea here is that we want that the total dose, that is the matrix product of that beamlet matrix with the spot weight vector, will, like when we do this calculation, the total dose will answer to the clinical goals that we have set at the beginning. And so in the equation, this is what we have here on the left down corner. We have the total dose in a voxel I is the vector product here. And so the idea is that we need to optimize the spot weight so that the resulting total dose will correspond to the clinical dose. So this slide you have already, if you were attending the demo that we did 2 months ago, we have already shown it. The idea is that we have like reproduced these 3 stages in our OpenTPS software. And as you can see, what do we need for optimization? We need the CT image. We need the structure, the artist struct. And once we have these 2 inputs, we can do a plan design. To make a plan design, we define Gantt triangles, couch angles, layer spacing, spot spacing, target margin. Then we set objectives on in our plan. Then we can launch the spot placement. At the end of this stage, we have our plan. But this plan is still empty, right? Because I mean, it has this list of spot X and Y Gantt triangle energy layers, but the spot weights for the moment are all set to 1. And so we need the optimization will tune this weight. Once we have this plan, we send it to MC square. And then MC square will, based on that plan, will produce the beamlets. Now we have the beamlets and the plan, we can send it to the plan optimization process that will wait. And in this process, what we have to do is to specify the solver that we want to use. So as Sylvain already mentioned, we have different type of optimizer. We have this second order optimization, BFGS, but also first order optimization for convex non-differentiable objective functions, FISTA. We can also set a different type of parameters like the maximum number of iteration or the tolerance, the absolute tolerance on our functions, etc. At the end of this process, we have our optimized plan, and then we can send it again to MC square that will make a final dose calculation. This is what is interesting to us at the end of the day. So to illustrate optimization workflow, we have built this example on a brain case. Actually, this example itself is not available yet on the Git, but you have a more generic one on a water phantom that is available. But if we will probably make these slides available, so if you need to reproduce this example to do it on your own data, it will be really easy to do it for you. So I have this brain case. The first thing to do in our script is to import the CT image and the artist structure, right? So this is what I'm doing. I specify the CT image path. Then I'm just taking, I read the data at this path. I will extract the CT and contours, and then I will extract the ROI that are interesting to me. So CTV, optic chiasm in this case, brainstem, brain, blah, blah, blah. Now, as I said, we need to design the plan. So in this slide, I have put in parallel in the GUI and in the core. So you have the scripting on the right and in the graphical user interface on the left. So you see that you are in the plan design tab in the GUI. We can specify a plan name if you want. You have to specify the path to the scanner folder BDL. Then you will specify spot spacing, layer spacing, target margin. If you want proximal layers, distal layers. So this is these lines. On the right, it's all the same. I mean, it's really easy to make it correspond. You can see here, this is where it is written. And then I create the plan design here, an object plan design, and I will attribute to that plan design like this. Then you have to add your beams to your plan, right? So you just click add beam and you can specify the angles if you need a range shifter also. Once you have your beam set, in this case, I have set 3 beams, again, triangle 90 degree, couch angle 0, 270 and 315. In this case, it's written here, as you can see. I first instantiate 3 objects and then I put it in the plan design here. So you can also use robustness in your plan optimization. To do this, you have to modify the robustness settings. So we have this big button here. I will come back to this a little bit later when I will talk about robust optimization. But anyway, so you do this and then you click on design plan. In the script, what you have to do is that you set plan equals planinit.build plan. It will make the spot placement. Okay. Oh, and actually here on the right, what I included is the plan pencil text. That is it's an input for MC square that is generated automatically when you create your plan. So as you can see, you have it's really the plan description. So the number of fraction, number of fields, again, triangle, couch angle, energies, and then the spot weight. And as you can see, at the moment, all the spot weights are set to 1. So now, plan optimization. So the idea here is to first set the objectives, right? So this is what we are doing here. We open the objective panels, and we have all of our contours that are listed. And you just have to click on the cell that you want to modify. For example, if you want a D-mean on the CTV, well, you just select the cell, type your value, and then just enter, and it will directly print on the plan optimization tab here on the left. In this case, I have added 6 objectives with various weights, as you can see, and a min and max on the CTV. And now you have your objectives, you have your plan, so we have to select the optimization algorithms that you want to use. So how you do this? Well, this is, how do you call this? Menu déroulant. Scrolling menu. So you click on it and you will see that you have a couple of different optimizers. We have put this one SciPy LBFGS as recommended, but there are others that you can use and try. So there is also a button advanced configuration. This is where you can set the number of max of iterations. Also, you can set bound constraint on the spot MU. If you know that your machine cannot go above 5 MU or something like this. And so then you click OK. You select play spot compute beamlets because this is the first time you create a plan, so you need to do all of these steps. And then you can select optimize plan. What will happen there? Well, first it will freeze. Don't panic, it's normal. It's because actually the spot placement in the GUI is done at this step, and it's because before the spot placement and the ray tracing operation happens, you have to delete your target with the target margin that you have specified in the plan design, and this takes some time, unfortunately, for now, because just that the function available in Python takes time. But so you wait a little bit, and then a new window will pop up. What will happen is a beamlet-based configuration will pop up, and this is where you specify the settings for the beamlet computation. So the number of particles, the scoring spacing that you want to use. If you want to use the cropping of the beamlets on the region of interest, because if you crop, it will when you import the beamlets. So the simulation statistic, etc. So this will pop up automatically. So just set your parameters, and then you just select compute beamlets. So at this moment, the GUI will again freeze. That's normal. Depending on the IDE that you are using, you will see something in the terminal or not. In PyCharm, I see the simulation of each beamlet, but I know that in Spider, we were not able to see that output, MC² output. So it's something linked with C code or something. But so just wait. Unfortunately, for the moment, we don't have any progress bar, but this is something that we want to implement to like relax people when they use the GUI. So the beamlets will be simulated, then they will be imported, and then the optimization will launch directly after. And then it will just stop, and the result will be stored in the patient data. So I was talking about the GUI, but now what does it look like in the scripting? Well, again, this is how you set objectives. So you create an object called objective list. You set the target you want, then you add an objective on whichever contour you want. And then you can instantiate the method that you want to use to optimize. In this case, I'm just using SciPy, and this is where you set the number of iteration, or there are other parameters, but this is more for developers. They can look directly in the functions and see what parameters they can use and modify. And then once you have instantiated your optimizer, you just launch solver.optimize, and here we go. Actually, I didn't put the beamlet. Oh, yes. Okay, sorry. Because I was showing you in the GUI that you have to place the spot and then launch the beamlet computation, but you have also to do it in the scripting, right? And this happens just after the spot placement. So you have this function build plan, and in the script to launch the beamlet computation, it's just mc².compute beamlets. And then you put the beamlets in the plan design for convenience. It won't work if you do not. And so this. So we have optimized our plan, and just a few words on the different solvers that you can find in OpenTPS for the moment. So all of these are to optimize IMPT plans. We have these second order methods that use the Asian matrix, SciPy, LBFGS, BFGS, and also an in-house implementation. We have
sorry, I don't speak German. Do you know
included that
English?
in-house implementation because because the SciPy implementation is sort of a black box.
Okay.
And it's not easy really if you want to change stuff inside the algorithm.
Yeah.
So if you want to play a little bit with the algorithm, like change, for example, the line search that will optimize the step size at each iteration, you can go and look at this implementation and modify to your will. Then we have the first order methods, like the basic gradient method. We have the FISTA also method that is really nice when you want to add new objectives to your objective function that are not, let's say, trivial objectives like dose fidelity. So you can, for example, you add a sparsity term if you want to reduce the number of spots during your optimization. So you would just have to add a new objective term to that objective function. I will show also an example later. And then we have this beamlet-free optimization that is more like a stochastic gradient descent algorithm. And actually, it does not require the beamlet computation, that algorithm. And finally, we have also another type of solver that is based on linear programming. And as said Sylvain, this one requires a Gurobi license. And it's pretty nice because you can also do a mixed integer programming and like build your own model with your own function, etc. Pretty modular as well. So just a few words on the bond, like if you want to use the bond constraints on your spot MU, in the GUI, I show you that it was that line that you had to change if you want to do this. But in the GUI, actually, you have to use not the IMPT optimizer, but you have to use the bond constraint optimizer. The reason why we have not just implemented an argument inside IMPT optimizer that says, okay, I want bonds between blah, 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 and blah, 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 is because this bond constraint optimizer performs two optimization consecutively. And so we had to implement a completely new optimizer to have this feature. And this feature is only available for SciPy and BFGS for now. But if you want to use it with FISTA, the workaround is just to add a new objective term that will project on the interval that you want to project the spot weights. Few words on the FISTA optimizer. So actually, it is not our own implementation, the FISTA. You will see that there is also the license of Pionlog box. That is a package from EPFL. So it's a really nice package that allows to do a non-differentiable convex optimization problem. You can add any number of terms to your and so in terms of application, as I said, spot sparsity, layer sparsity, energy sequencing. So for example, for proton arc optimization, which is my research personally. So it's very convenient. And this is how you use it. So you create you instantiate your IMPT plan optimizer, but you specify the method to be FISTA. And then this is after you instantiate a new function. Like, for example, in this case, I just created a L1 norm and a positive projection. And then you just have to add these functions to the solver. And it will understand that there are more than those fidelity objectives and optimize with this new function. So all of this, you will find it in the core processing plan optimization folder, and you will see we have like 3 main folders. we have the solver folder here that contains FISA, BFGS, etc. We have an objective folder where you can find norms function, projection functions, dose fidelity, which is the most important for radiotherapy. And then finally, also a folder that contains all the acceleration for it's like optimization, basically. And I wanted to show you this because this is where you can, if you want, add your own optimizer or tune the one that already exists. So now what's the output of the optimization? So on the left, you have in the GUI. So you remember I made that plan on the brain case with 3 beams. And so that's the result. I have also check the box of the contour that I wanted to see. And you have the dose displayed there. And I clicked on that display, the DVH. So you also, something that I noticed is that if like when you first optimize, sometimes the color scale will be very high because there is some noise in the dose calculation. So you have to normalize your image to your dose prescription. And you can do this by going to tools, secondary image, then there is window level, and you can just set your max dose level to your prescription. On the right, this is what happens if you run like simple optimization. For example, I mean, the simple optimization example, but this is for the brain case, and you see that it just displays these plots of Python of the image slice with the dose distribution, and on the right, the DVH. And we have also included in the script a function that will print like a clinical evaluation of your dose at the end of the optimization. And it will display like the list of contour that you want to study, metric that you wanted to see, the limit that you have set, and then if it passed or not, the goal. Maybe in the future, this will be also included in the GUI. And right now, actually, in the GUI, if you want to see these numbers, the thing that you have to do is just to put your arrow on the DVH curve, and it will display the D95, D5, and D-min. Robust optimization. So what is the robust optimization that we have implemented in the OpenTPS is a scenario-wise worst-case optimization, so sort of a min-max optimization. The strategy is error space. So we have 21 scenarios that are simulated, 7 setup times 3 range. So in the terminal, what we will see is that it will simulate scenario by scenario. For like, we have one set of beamnets for each scenario generated. So this takes a lot of time. In the GUI, the only thing you have to do is that you have to set the robustness settings in the plan design, and then you have to select here, when you set the objectives, the little box robust, if you want your objective to be robust. Okay. So I put here a RayStation screenshot just to compare a little bit, because this is what people are usually familiar with. And well, it's exactly the same, you will see. Very intuitive. Exactly the same. Yes, what? Anyway, in the script, how does it work? Well, you have to create like you have to instantiate the attribute of robustness of plan design with the different setup, systematic, random, and range error like this. And basically you select your selection strategy here. And then instead of mc².compute beamlets, you have to write robust scenario beamlets. And then, yes, you set the beamlets to be the nominal and the scenarios that you have just generated with that function. And for the objective, like you remember in the GUI, there was this checkbox. Well, in the script, the only thing that you have to do is to add here an argument that is robust equals to true. Robust evaluation now. So we have this tool that allows us, when our optimization is finished, to evaluate the robustness of our plan. It was implemented by Marie Coelis when she was a PhD student in MIRO. So she designed like two strategies, error space or dose space. If you use the error space strategy, it will generate 81 scenario. That is actually just the combination of all the setup and range uncertainties. If you want to look at dose space evaluation, well, you set just it's a random scenario sampling. So you set the number of scenarios that you want to generate, and then you give a confidence interval on which that will select the, for example, if you set a 90% confidence interval, you will select the on 100, the 90 best scenario. And in the terminal, it will just display these lines: robustness simulation, scenario 2/81, and etc. It's also a pretty long process to simulate all of these scenarios because you have to compute the dose each time. And at the end of the day, we have this beautiful plot with nominal and DVH bands. So as you can see, the DVH band in my case are pretty big because this plan was not optimized with robustness settings. Okay, last slide on optimization. Just tips I wanted you to have. So as I already mentioned them a little bit, but as I said, depending on the IDE, MC² output will not always be displayed. Optimizing a plan is a slow process, especially if you have like a very big tumor or things like this. So yes, that I said, target dilatation is also slow process. We have no progress bar, so if it freezes, it doesn't mean that it's a bug. It just means that it takes its time. So I just recommend to look with the htop command if it's still running, or in Windows, just look at the task manager. After the optimization, the dose for the moment does not display automatically. So you have to go in your patient data and double click on the dose image that was produced. Yeah, at the end of the optimization, you have all of these, you have the plan, the dose image, and this is how you know that it worked. And again, the DVH does not display automatically, so you have to press on that little button in the GUI. And I wanted to just say that OpenTPS is in continual improvement and be indulgent and make issues. If you report a bug, we will try to do our best to correct it in time. Voilà. Thank you. Let Guillaume talk about image processing. Oh, any questions? Yes. Yes. Yeah.
And if you put random error,
You mean for the robust optimization then?
Instead of 0, I put millimeters. 21 scenario or 21 is 0 and 20.
No, you will have
Sophie,
21 with 2.
Sophie, we don't hear the question online. Could you repeat?
And the nominal. Any other question?
Yeah, in the chats, Lucien asked, what is the output format of an optimized plan?
So you can save it as a DICOM plan if you want. Export it as a DICOM plan, but
I don't think it would.
in the GUI, but in the scripting it works. On my side it works. Okay, apparently there is still some question to solve here, but we should have a tool that allows the export in DICOM. And you can also save the plan in OpenTPS format that is like .tps. And just by using which line? Here, save RT plan 5. So you will have this OpenTPS format that you can reload in your script. Same for the beamlets. There is also a function that allows to save the beamlets. I have not displayed it here, but you have a saving tool. Yeah, and Kevin is saying DICOM and C-square and OpenTPS format. Thank you.
Sophie. So the next part will be about image processing. So OpenTPS is first about plan optimization, right? Why it's called OpenTPS. But we've also worked on other, I would say, applications that uses the same tools, but that needs more image processing as well. And so basically we have 3 categories of tools. We have all the basic image processing tools in such kind of softwares, like resampling of images so that you can put them together, filtering of images, fine transformation, deformation, etc. So really the basics here. We have also some basic image segmentation tools, and they're not for clinical evaluation, but they're very practical to be used in workflows. For instance, automatic body, bones, and lung segmentations in CT images. If you have a CT that doesn't have contours, but in many cases you would like to have, for instance, just a cropping around the body because you gain a lot of time. That's the kind of basic tools that make our lives easier, and they're available. And obviously all the morphological operations to change the size or erode and the masks. Then we have also some state-of-the-art image registration tools, so rigid and deformable, mostly daemons and morphons, and I will a bit describe afterwards what that means. So regarding the CT segmentation, it's pretty straightforward. You can see there on the right where it is in the where it is implemented in OpenTPS. If you want to use it, it's quite simple. You just import the segmentation. Here it's an example with segmentation CT, and then you have just one command for each kind of segmentations. You're just an example of results. So it's the kind of tools that are not they're not very complex AI-based methods, but they're quite practical to build some workflows. And to get quite quickly a good result. Then we have deformable image registration, and as you may know, we've worked a lot with image registration in UCL, so MIRO and ICT, as well as IBA. And so a lot of our applications are already based on deformable image registration, and most of them use OpenRegui. So in the past, we used OpenRegui for a lot of cases, and mainly based on these methods that we published a while ago, diffeomorphic morphons. And so in this framework, actually, we like to work with diffeomorphic deformations. And that's the reason why in OpenTPS we decided to model a deformation by actually two fields, a velocity field and a displacement field. The two are linked, so you can compute one from the other if you want, but it's very practical to have both. Actually, because on velocity fields, you can perform all algebraic operations. You can make the inverse of a field of information. You can sum transformations. You can make the average or amplify a transformation. All these operations you cannot do on a displacement field. But when you have to deform an image, you need the displacement field. And actually, what ensures the diffeomorphism is just that the displacement field is the exponentiation of the velocity field. And that's why the object here, a deformation, contains both a velocity and a displacement field. They do not need to exist both, but we still have the two objects existing. And just here, I put a small example that I find quite explanatory to explain why we cannot use the displacement fields if we want to make operations on them. Here you have on the left two rotations, but that are described as displacement fields. So the displacement fields are the dark arrows, and the velocity is the light arrows. If we want to make the average of those two rotations that are, one is clockwise and the other is counterclockwise, well, the average of the two transformation is actually just the circles staying at the same place. So it is you can do that by just averaging the velocity fields. So if you average the velocity field and then from the velocity field you recreate a displacement field, the displacement field will be zero everywhere. If you do that directly on the displacement vectors, you can see that you have actually a shrinkage. So the average of rotating in one direction and in the other direction would result in a shrinkage, which is actually not what we would expect for the average of rotating into different directions. So that's just a simple example to explain why we use this complicated velocity plus displacement field model. So as I said in the past, we've worked a lot with this framework in OpenRegui. We have a lot of publications that are using those tools, and so we found it quite convenient actually to transfer those tools into OpenTPS, and so try to have really an equivalent of what we used in the past in OpenRegui and to have that in OpenTPS. That's what we did. So you can see again on the right where it is located in OpenTPS. And here a simple example on how to use it. So you just create an object, a registration. Here's the morphons, the diffeomorphic morphons. You give the fixed and moving images, and then you just compute, and you will get, as a result, the deformation between the two images, so velocity field and displacement field. And the results are there. You can see that there is almost no difference between Regui and OpenTPS. So small numerical differences, but not significant ones. So one thing that we worked with a lot as well, and that is based on deformable image registration, is actually the modeling of 4D sequences. So what we call here deformable 4D respiratory modeling. Also, we have some very early publications on which a lot of others were based. So to briefly explain what it is, usually when you work with your 4D data, you have when you work with breathing modeling, you start with 4D data, and so here it's an example of a tumor that moves, and there are 8 phases in the breathing. We can perform the deformable image registration between one reference phase and all the other phases of the cycle. And usually what we do is to compute the mid position, and the mid position is the average deformation of one of these reference phase, the others. So it's this average transformation is again computed using the velocity fields, because you cannot apply the same operations directly on the displacements. But so we get this average transformation that provides the mid position of the tumor. It's deformable, so here only one point is represented, but actually you have that for all points of the anatomy. And then you can back project. Well, you can first deform all the faces to the mid position and the mid position image by using just the median intensity value for each voxel. And then you can also recreate a model from that. So you can back project the mid position to all faces, and then you recreate what we call a model of a 3D dynamic model. So here just an illustration. On top you have the 4D CT. On bottom you have the corresponding 4D model. So it's the mid position image deformed back to the different phases of the breathing. Again, that's a tool that we've used a lot in the past. And so we have already so a lot of publication based on that, and so we found it convenient to keep the same tool now in the new platform, which is OpenTPS. And to use it again, it's not very complicated. So you can see on the right where it is located, the mid position function. And basically, if you want to create a dynamic 3D model, you can just create the object and then apply the function compute mid position image on it. The output will contain the mid position image as such, and also a sequence of deformations towards all the phases of the breathing. So all phases of the initial 4D CT. And again, that's a result. So here you have the 10 phases of a 4D CT. You have the mid position computed by OpenTPS, the one computed by OpenRegri, and the differences are very minor, so they're not significant. And with that, I conclude the image processing part. Any question?
Some Lucian asked if the image processing tools are available in the GUI or only scripts.
So some of them are available in the GUI, in the sense that you can, in the GUI, you can create. Well, first there is a registration tab, so you can indeed access the registration, and then for the last part of the respiratory modeling, you can also convert a 4D CT. So if you have a 4D CT from the interface, you can create this 4D model, or this 3D dynamic model.
Segmentation tools are also right. We used to learning segmentation.
They used to be the GUI, but not for the major refactoring. So I asked a question if this would be an important feature
Yeah, we haven't.
You suggested we could do a wish list.
Yes, yeah, that would be nice to have this wish list so that we understand a bit what are the needs that are still not met. Obviously, we cannot commit on implementing all the wish list, but it would be interesting indeed to have a wish list somewhere where we understand what are the main needs.
So the question is, are those registration approaches able to register a 2D image like a radiograph or DNR to a 3D one? So 3D registration is available.
No, we have no methods for that. So what we have implemented so far is only 3D to 3D. We don't even have, well, the method is, exists for 2D, but we haven't transferred that part yet in OpenTPS. Yes.
Where is the file saved at?
So at the end, you have all the data that are stored in the patient list. So the mid-position CT, you can obviously export that into DICOM. For the moment, we haven't implemented the vector field exports in DICOM. So it's still something that we have to do. So we will do it, but it's not yet available.
The 3D model, where do you put it?
So it's in the patient list. So I would say inside OpenTPS, it's the binary format of OpenTPS. So you can look in the structure of the object that is described in the Python code. But there is no export into files at the moment.
I think it's serialized.
Yes.
So if you use always the same model, you can save it as a serialized object. And this one we will be able to reload after.
Yeah, so you just export the binary version of what you have in the OpenTPS. Okay, thank you.
Hi, so I'm Damien. I will complement a little bit what Guillaume said with the data augmentation options. AI domain, because in AI usually you have data sets and you want to create more data to represent more little variations of your data, small rotations and things like that. And in our case, that's what we want to do also for patient-specific application in the breathing for a mobile target. So we have this patient, he will breathe a certain way, and we want to simulate different breathing patterns, different setup errors in the table and things like that. And so for that, we have this data augmentation tool, which is specific to a patient for now. So what we want to simulate are the interfraction and intrafraction motions. So the interfractions are the uniform transform, like the setup errors. The patient will be a little bit tilted on the table or translated or things like that. Baseline shift that can happen on the target, but also maybe organs, and shrinks that can eventually happen on the target. It could be used also to evaluate the robustness of a plan after, because you can simulate these different transformation and then compute the dose on this image. The dose is still correct or not. And for the intrafraction, we can simulate different breathing motion. Baseline shift can also be used in intrafraction, and it can also be used for robustness or interplay evaluation. There are examples of these tools in the core example folder, dynamic data subfolder. For example, here, baseline shift. So there is a target here, And I shifted it a little bit in this direction. So X positive or negative direction, I'm not sure. And so you see target is a little bit shifted, and it still looks like a CT image. I think a doctor cannot really tell the difference, but it can be different little, let's say, errors happening sometimes on the borders. If you have something moving, it could eventually draw the different structure that you have created, because it uses the deformation fields to move a part of the image. So to use that, you need the mask that you want to shift. You have your shifted image and shifted mask, which is the return of the apply baseline shift data mask with the baseline shift. It can be in 3 dimensions. You can apply, for example, this function on 3D image or 3D model, because if you want to make a patient breathe differently after the baseline shift, you have to deform not only the image, the mid-pay image, but also all the deformation fields in the model. Another example is a shrink. So here the same image, the same targets, it is a little bit shrinked. So it's more difficult to represent a real shrink that can happen in a target with image processing. So we have a function to do that. I'm not sure it's really clinically representative, but it can be used also to evaluate different frameworks. And then classical rotations and translations. So here an example of what we can do to rotate the data. This function can rotate an image 3D, a vector field, dynamic 3D model, or dynamic 3D sequence, which are data types representing the model. And the dynamic 3D sequence is just like a 4D CT, so it's a sequence of 3D data. And the same for a little translation here. Now, in my team, we work on AI projects, and yeah, rotation and translation, sorry, are also available as affine transform. So there are two, let's say, 2 places in the core package that you can access these transformation. There is also in the core processing, image processing, SITK image processing. Here there is an apply transform that can apply an affine transform to an image. But it is not available now for deformation fields. So that can be applied on images, but not on deformation fields. And in my team, we work on intrafraction changes also, because we want to create all these little variations that the patient could have during a treatment, including the different motion possible. So what we do is that we create more images from the 3D dynamic 3D model that Guillaume presented, thanks to the amazing diffeomorphic morphome algorithm. Using the velocity fields, we can do that really, let's say, easily. There are a lot of research years, it becomes easy. So what do you make a model? Guillaume already showed you. You can just compute the model here. This needs a dynamic sequence. So 4D CT, and a 4D CT, you can create it like this. So you read the data to a 4D CT folder, and then you create a dynamic sequence and you give it the list of images just to create, let's say, a linked 4D CT. Then you create a model and you compute the image. Then when you have this model, you can create synthetic breathing signals, which are in core data, dynamic data breathing signals. You have a lot of little parameters that you can add to create these signals. It has been written by Gauthier, which is here somewhere there, to simulate a breathing signal. So you can add more noise, you can add apnea, you can add different things to make a breathing signal regular or not. And then you can choose somewhere in the anatomy and a direction in which you want to apply this motion. So here, for example, I choose 2 points and I apply 2 different signals. So on this point there, on the liver, I apply the blue signal. And on the orange one there, on the other side, I apply this one. So it's opposite of the blue one. And then at some point, it doesn't move anymore. And thanks to a combination of different velocity fields, we can make the patient breathe this way. So we can choose any number of points and apply any number of signals, motion signals, to create any number of respiration, breathing motions. So of course, this is not realistic. You cannot really breathe like this. It's not possible, but it's just to show the example of how we can use this to create more data from a dynamic 3D model. Because the real issue with mobile targets is that 4D CT are acquired one day on a 2-minute, 3-minute long acquisition. It represents one average breathing period. And then you can have a lot of different changes between this acquisition and the treatment day. So it's important to be able to model more different, let's say, configurations and possibilities for the breathing of the patients. Yes, that's it. So these dynamic 3D images can be shown in the GUI. I think you mentioned that it wasn't, but I think it is working. So you can show dynamic images in the GUI as well. That's it for my part. Is there any questions? Right. So now for next part, Valentin.
Okay. Okay, so now I'm going to talk a bit about so how can we evaluate the impact of motion? So simulating a plan on a patient which has a tumor movement, and for this we did several kind of simulations. So the first kind of simulation we can do is what we call the 4D dose simulation, where we independently simulate a treatment plan on each motion phase of a 4D CT, and then we compute the average of this dose. And here we suppose that the plan is delivered statically, so we neglect here any interplay. And in this simulation, you just want to evaluate the effect of the range variation with motion. So that's the first kind of simulation you can do. And then another kind of simulation you can do is a dynamic dose simulation, where here you simulate really the plan spot by spot with a time delivery model. So at which time each spot is delivered, and then you can simulate this on a sequence of 3D CTs. But in general, you would simulate it just on a looped version of the 4D CT. So you have 10 images, and then you suppose they repeat over and over. And so yeah, and this kind of simulation is used to evaluate the interplay. And then you can also, of course, look at what happens when you have a different fraction, how this is statistically averaging, etc. So first for the simulation, so for the dose simulation, where we neglect the interplay here. So what you have as input is just, so you have a 4D CT, a sequence of, for example, 10 CTs. Then from this in OpenTPS, you can construct a 3D model like we talked about. So you can create a mid-position image and then the associated deformation fields. Then you have a plan that you have already optimized. And then you can compute the dose of this plan on each of those CTs. So you obtain 10 doses if you have 10 CTs. And then from those 10 doses, you can deform those doses to the mid-position CTs. And then you can finally add them or average to a final dose, which represent your final dose and how and what is the impact of this proton range variation. And then, yeah, you can obtain a DVH where here you have 10 doses, and so you can have an idea of the uncertainty in your DVH. And looking at the code, it's quite easy if you already have a plan optimize and a 4D CT, then you can just create basically an object, which is called plan delivery simulation, and then apply this method, simulate 4D dose. Then next kind of simulation is the dynamic dose simulation. So here we take into account interplay. So we start with the same kind of input as before, but we add we need a delivery model now. So we need to know, okay, so we have all those spots at which time each spot is delivered. So at IBA we have what we call the scan-algo algorithm, which is proprietary software, which would give us the time delivery of each spot. But of course, we can also implement your in-house model if you want. For the moment, only the scan-algo algorithm is what is the code is interfacing with it. Then from this, you can get your RT plans with the timings of each spot. And then you imagine that you have a patient motion model. So in the case of a 4D CT, it's just the same. You suppose it's the same breathing cycle that is repeating over and over again, and that each duration is the same. So one CT will be 1/10 of the time in the case of a 10 image per CT. Then what you do then is that you split this plan in 10 plans, actually, and each plan contains only the spots that are delivered in the breathing phase that correspond to this plan. Okay, so you have one plan associated to each CT, and each plan contains a subset of all spots. Then you simulate the dose on the CT. You obtain the dose, then you deform it back to the mid to the mid position CT, and then finally you can add all those doses. So note here that you don't have to multiply by 1/10 because it's only a subset of each spot for each dose, and then you obtain this 4D dynamic dose, which evaluate the interplay. And you can also do it quite easily in the same way as before the code. So it's another function, but of course you can also provide some more parameters, so the breathing period and things like that you can play with. Yeah, and now so what about different kind of scenario? Because for the moment we so in the previous slide that's just one possibility. You have multiple 4D dose possible. So one way to assess different dynamic dose is just an easy way to do that is starting the delivery at a different phase each time, and then you get 10 accumulated dose, but actually it's not 10, but it's so for each simulation you need to compute 10 partial dose, so the dose corresponding to each motion phase, and then if you want to start at different time, so you multiply again by 10, so that 100 dose computation, so that can be quite some time consuming. So you can also set a parameter to choose the number of starting phases that you want. And yeah, here for example, you can also provide a DVH with this uncertainty bound like before, and then you can also see, okay, what's the impact of having multiple fraction. So here it's just summing X number of fraction. So if you have 5 fraction, you have 5 dose. And there is also many scenario possible here. So either so you can see it as a combination with replacement, where each so if you have 5 fractions, for example, well, you can have a dose which starts from phase 1, a dose which starts from phase 3, again from phase 3, etc. And there's many combinations possible. So you can also provide a parameter here where you decide the number of scenarios that you want, And then in the end here, with those 3 parameters, you can compute several dynamic dose simulations. Yeah, and I think that's it. I don't know if there's question here. It was clear. Not in the chat. Okay. So I will let Sylvain conclude.
Today we have covered many different topics, I think. And the last one I would like to present today is how you can get started with OpenTPS. And also for those who are interested in how you can do OpenTPS. I think there are very different people. Some would just like to test it, to try to use it. So what we do is that we strongly advise you to clone the project so that you can always pull the latest version. The OpenTPS is a project which is evolving a lot, and there are commits every day. So we're also fixing issues every day because it's a very young project. So it's better to clone the project and to prove the changes maybe every day. On the OpenTPS, so there are 3 roles for people who use OpenTPS. You can either be a maintainer, so this is the case of myself and all the main developers of OpenTPS, so the people who spoke today. Then if we have a very close collaboration on a specific issue or a specific feature, we can add you as a project member. So you are a direct contributor. This means that you have direct access to the Git. You can commit, you can push, you can create new branches. And for the others, you are just a non-project member, so you can clone the project because it's public, so everyone in the world can clone it, but you cannot push to the project. So this is summarized here. Everyone in the world can clone and fork the project, but nobody can push to master, so there is a mechanism which prevents this. So if you want to submit a feature, an enhancement, a fix, whatever, you have to create a branch, commit to that branch, and then ask us to make the merge into master. And only the maintainers can merge branches into master. And you have to be a project member, as I said, so you have to be registered on the GitLab to create a new branch. So we have started integrating some automatic tests. This is only the beginning. We don't need to buy a new server to run those tests on the server. So the idea is every time you push, there are some tests which are run on this server to ensure that there is no regression. But currently, the number of tests is very small. We only test a few things, but the most important one. And we plan to implement more and more tests in the future. And so there is a protection mechanism which automatically prevents branches or failed tests to be merged into master. So that's why it's very important to us to add more and more tests. Yeah, I wanted to point out as well that GitLab has a very nice web interface where you can see absolutely everything related to the Git and also to those tests. So if you push, you can see the results of the test, and you can also see where it failed, if it failed. So if you are project members, we are in this very close collaboration, or you're part of the team, and you want to develop new feature in OpenTPS, this is the way that we do. The first thing that I strongly advise is to create an issue. That's not mandatory, but that's that would be great, because in this issue in the GitLab we can have a discussion. People can comment. And you can also describe what you are doing, so there is some kind of traceability of your idea. We can also reopen the issue if we find that it was not actually done yet. So that's a very good practice to first create an issue, and then to create a branch and to link that branch to this issue. And from the web interface, you can do this very easily. There are a button to create an issue, and then there is a button to create a branch linked to that issue. And then you work in this branch. And when you're done, your work is done, you can just request your work to be merged into the master branch. For people would like to develop in OpenTPS, but let's say we are not in a close collaboration, or are just investigating, they already don't know what they will exactly do. It's not a very clear idea. The best way to do is clearly to fork the project. So you have a copy of the project where you can do your stuff, and this won't impact the original project. And if you have something great, useful for the community, or you fixed something, for example, you can create a merge request. So you can ask to merge the changes into the original project. There are plenty of documentation on GitLab. And there is a particular reason we don't want too many contributors to access directly the Git, is that we need to keep the size of the project small. We need to keep the control, and especially we need to prevent from having things like temp data pushed on the Git, temporary files, this kind of stuff pushed by mistakes. But it's extremely complex to clean a Git history, because Git is really not made to be cleaned. It's made to keep the history of everything. It's a very complex task, so we really don't want to do this. And so this is a very clean way to work, to fork the project, a very safe way. I found a very nice diagram on the web, which shows how this works. You have the official OpenTPS repository on the left. You can fork the project, and you can always pull the latest version of OpenTPS in your fork project. And you can also ask a merge. So it still works both ways. You're on a separate project, so you don't modify the history of the original project. And there on your fork project, of course, you work the way you like, but usually create some feature branches and commit to those branches. Okay.
Questions for the...
Yes, right. Before, are there any questions related to how to get started with it, how to contribute with it? So this afternoon, for people who would like to attend, we will have a practical session. So this means that we are in this room. So we can help you get started with OpenTPS. If there is some issues related to the installation of OpenTPS, we can have a look, and then we can also have a look with you on how to run examples, etc. For people who would like to discuss a bit more in details whatever we have said today, don't hesitate to send an email, and we can also have a discussion, a meeting later. I think that it will be difficult to have an online support for this afternoon session. But if you're only a few, we may try and we see how we can do it. So we have time this afternoon to answer questions. So don't hesitate to connect or to send an email, and we see how we can do it. So questions in the chat?
There was one question, but already answered.
Yeah. Hello.
Kevin?
Hello. Can you hear me?
Do we need our own GitLab if you want to fork OpenTPS?
Hello. I don't think they hear us.
Yes, I think
So
that
yeah,
we're actually cut out.
currently OpenTPS is hosted on the official GitLab, gitlab.com website. So you can create an account on this website and you can form the project on this website. And the reason why we should GitLab, and we've been working with GitLab for a long time, is that it's the only platform where you can have private, free private repository. For example, on GitHub, everything is public. So you create a project on GitHub is public, but on GitLab it's not. And that's a very main advantage. So if you want to develop things which you think are private, maybe because not published yet, or just that you don't want this to be public, you can do it on GitLab. And so you can fork the OpenTPS project on GitLab, and I think that you can make it private, so no one will see it. Of course, this is an open source project, so if you please, if you have nice features, if you have nice stuff to merge, don't hesitate to contact us, and we try to make this project become bigger and bigger. That's really the idea, that everyone benefits, and that prototyping in radiation therapy is even much faster.
You can also use your GitHub account if you already have one. I'm using my GitHub account to.
GitLab?
Yeah.
Okay, so Sophie said that GitHub, the GitHub account is compatible with GitLab. That's nice.
Someone is trying to ask a question. Can you do the sound? Or do you need to?
Do you hear us?
Yes, we do. Yes, we do. Yes, we do. Yes, we do. No, no, no.
Sorry. Just hello. Hi.
I am okay. You can.
Okay. Hello.
Hello.
Yeah, I'm trying to figure out if I can get through.
We are ready for the question.
Hello.
Hello.
Hello, Kevin.
So
I'm just trying to.
I put my question in chat also.
Okay.
Yeah, so I don't know whether we can. I mean, no, apparently we can even talk. So I was thinking to even try to somehow also include the remote people. I mean, it might be good just to have a session, you know, either on our own or no. I don't know how much help we actually need from the team, but it would be good just to, nevertheless, even though we're remote, still try to run through some examples and then just maybe occasionally. So I don't think we would need help all the time, but just occasionally maybe some help. I don't know.
Sure. So don't we will connect to the meeting. Don't hesitate to write in the chat if you want help, or if you want that we look at something together, and we'll meet in the at the time. Is it okay?
Yeah, so if we would have just maybe instructions shared, or, you know, just the general ideas, and then we would just try and, you know, do the examples, and maybe if we get stuck, then maybe we can even talk online, because there's other people who can just share ideas remotely as well. And then if we, you know, if we come to a roadblock, then we just scream or something.
Yes, we will. We'll do like this. We will share the instructions at the beginning of the session. So I think 2 o'clock or 1:30. I don't remember. 1:30. I say 1:30. Okay. We'll do it. So yeah, once again, thank you all. Wasn't expecting so many people. That's That's really nice. Thank you very much. For those who are in Louvain-la-Neuve, I think there should be sandwiches for everyone. And then we can meet at 1:30 for this practical session, and we'll share the instructions at the beginning of the session for the people who will join us remotely. Thanks again.
Outside. But yeah, it's okay here, but not drinking.